All right, so streaming is done, and we are just going to get started here. All right, so what we'll do today is to introduce the next lab activity, which will start today. But instead of explaining exactly how to do the lab, we are going to talk about the concepts. It's activated already because one of the students in this class goes to the Monday, Wednesday section, and that person has, so the Monday, Wednesday class is once again just slightly ahead of this class, so they have caught up already. So which is good because that means if you want to listen to a slightly different lecture on the same topic, you can actually watch the other class too. Okay, sometimes it's helpful. So this is your next lab for this class. It's basically making sure that you have a good understanding of these three instructions. One is LD for load, one is ST for store, and one is LDI for load immediate. So those are the three instructions that this particular lab is going to focus on. But in class today, we are only going to focus on one instruction. In the Monday, Wednesday class, we focused on LD already, the load instruction. So in this class, I'm going to focus on the opposite, which is the ST instruction. Okay. So that means, if you want to have a good understanding of the LD instruction, one thing that you can do is to watch the video from yesterday, so you can actually get the part that explains the LD instruction as well. I don't think that is necessary because the two instructions are basically just opposites of each other. So if you understand one, you should understand the other one fairly well as well. So that's the general plan for today. And as usual, we'll need to use LogicSim for this. So let's go ahead and start up LogicSim. And I will also go to the processor right away and start up the processor. So it's processor. Okay, where did I put that? Okay, I can always start it first and then look for it inside of LogicSim. And this is a good time to double check, make sure that I am in fact streaming and the audio is good. So everything is checked. We go here, we open up the processor file, and it's not there anymore, it's in the temp folder. There should be another one in my own folder. There we go. All right, so this is the processor. So what we want to do today, and I'll just explain it using the C notation, and I'll put it on the side. I'm going to use mousepad here. So the mousepad is really just a notepad. I'm using it as a notepad right now to kind of document what we want to do. So what we want to do here inside the mousepad is, this is what I want to do. I'm just going to do it like this. D equals to B. Okay, so this is what we want to do. We look at register B as B. We look at register D as D here. So what we are trying to do is to store the value of register B to whatever location in RAM that register D is pointing to. Is that okay? So this is actual C syntax. I'm borrowing the dereference operator and the assignment operator from C and C++. So what we want to do is to say, okay, the location in RAM pointed to by D is going to be changed to the value of register B. Is that okay? Does everybody understand what I'm about to do? Yes? D is a register, but I'm treating it as a pointer. B is just, okay, so registers have no inherent types. So a register in the toy processor is nothing more than a byte. So should I look at it as a character, an unsigned integer, a signed integer, or a pointer? Hey, who knows? So it all depends on how you're using it. So in this particular case, all we're doing is to say whatever content register B has is going to be copied to the RAM location that is pointed to by register D. It is a dereference operator. No. The content of RAM pointed to by register D will be the same as the content of B after this operation. Okay? So you gotta kind of try to remember what dereferencing does in C and C++, when we deal with pointers and addresses.
But so unlike normal pointer, it's pointing instead of pointing to a location in RAM, it's pointing to a location in the register which points to a location in RAM, or is this how C works the whole time?
Okay, how about this? I'm going to go to the logic sim and give you a scenario, and then we'll explain how to make it happen. Okay, so I think that would be more clear. Okay, so I'm going to go back to I'm going to here, and before this I'm going to do some initializations. Okay, because otherwise D and B are all going to be zeros, which means it's not very helpful, not very fun. So what we'll do is we'll pre-initialize a few things. We'll pre-initialize register B to have the hexadecimal value or hexadecimal number of, I don't know, let's say 40 in this case, and register D has the value of 85, okay, in hexadecimal, okay? So after we carry out this operation, what's going to happen? Register B has a value of 40 in hexadecimal, so 40 is going to be copied to the location pointed to by register D, which means in RAM, location 85 in hexadecimal will now be updated to a value of 40. Okay? So if I were to do everything by hand, okay, so let's take a look at what this is involving if I do everything by hand. If I do everything by hand, then the first thing I do is go to the register bank, change the registers to have those particular values. Register D is supposed to have what again? Okay, register D is supposed to be 85. So 85 in hexadecimal. Register B is supposed to have value 40. Okay, so that's the first thing, to initialize the registers. And then the second thing I want to do, which is the only thing that I want to explain today, is the store instruction. So the store instruction is going to go put the value of register B, which is 40, into the RAM location pointed to by register D. So when you switch back here, register D has a value of 85 in hexadecimal. So what we want to do is to go to that location in RAM. So we scroll over to the RAM component, and we say, let's go to location, what was it again? I can never remember how I initialized the registers. So we want to go to location 85. Okay, so right click, go to edit content, go to location 85. This is 85 here. Now how do I know this is location 85? Because the byte all the way to the left has the address that is indicated in the leftmost column. So this byte is location 80, 81, 82, 83, 84, and this is location 85. I want that location to have the value of register B, which at this point is 40. So if I were to do it by hand, this is what I want to accomplish. Is that okay? I really hope that nobody comes from a background of Visual Basic or Java, because there are no pointers in those two languages. But there's a different way to look at this, okay? So there's a bright side to this. There's always an alternative. So the alternative to look at this is to look at RAM as a huge array. It's an array of 256 bytes. And you're using register D as an index, and you're changing that particular element indexed by register D so that that content or that byte location now has the value of register B. So that's the other way to look at it. So is that helping for those of you who did not have C or C++? So these two are quote unquote equivalent concepts, at least from the perspective of this class. Is that okay? All right, cool. So how do we get this done? In other words, if I am not going to do this and doctor the content of RAM manually, and I want the processor to do it, what do we need to do? Well, don't you think we kind of need to wake up the RAM component and say, hey, I want you to do something for me? That seems logical, right? Yes? Okay, so how do we wake up the RAM component? So I'm going to write down these steps, step by step as well. So we switch back to the processor design. This is the RAM component. How do we wake up the RAM component and say, hey, I need you to do something for me? Which port is responsible to do that? The select port, okay, SEL, okay? So SEL needs to be a 1, which means RAM cell has to be a 1. So we're going to talk about the values to the tunnels first. So I'm going to document that, okay? RAM cell equals 1, is to wake up the RAM component. We're asking the RAM component to pay attention, okay? I need you to do something. Okay, next, what else do we need to do? What is the clock cycle? We really don't have a whole lot of control over, so we'll just kind of skip over the clock. What about LD? LD is a port that controls whether we are reading from or writing to RAM. So if I'm writing to RAM, what do I need? Is it a 0 or a 1? A 0, very good. Okay, I see that some people either remember from last time or actually studied, or both. Okay, so RAM load is going to be a 0 to specify a pending write operation. Okay. Well, if you're doing something with RAM and you're trying to do a write operation, that should immediately raise two questions in your mind. Which location and what value? Does that make sense? Right? I mean, if you're writing to RAM, which has 256 locations, the next two questions will be which location and what is the new value of that location. Okay, so how do we control which location? What port of RAM controls the location that we need to access? A or D? A, very good. A stands for address, which is also used as quote unquote the index into the content of RAM. So we need A to specify which location. Which register again specifies the location? If I go back to the C notation, which register is responsible to specify the location that we want to overwrite? Register D. Okay, very good. So that means in the grand scheme of things, we want this port here, port A of RAM, somehow to be connected to register D inside the register bank, this guy over here. Is that okay? How many people as a kid, enjoy those puzzles where they give you a big old maze and you have to trace a line from one thing to another thing? That's what we're going to do now. Okay? All right. So we'll start with the A port of RAM and see if we can trace our way back to here. Okay? All right. So one thing about LogicSim that's kind of really cool is if you click on when you're in the poking tool and you poke a wire, it actually highlights where it goes to. It highlights the entire node. So we know the A port of RAM is connected to a multiplexer. This output pin is only here to display what is on the address bus, so it's not really that particularly useful. So it hooks up to a multiplexer. Tell me again, what is a multiplexer? What does it do? not so much combine as to select. It switches. Okay, it's more like a switch. So you can control which input connects to the output. The other input is just not. It's just ignored. Okay. Okay. So when we are connecting to a mux, then it becomes important to know which input has a likelihood of connecting to the register bank. Okay. So once again, if you use Logisim, it's actually easier because you can click on either wire and figure out where they hook up to. If you are just doing it, just eyeballing it, it's actually harder. Okay, so we'll explore this one here. And where does it go to? It goes to the PC. We'll explain the program counter later today. And it also hooks up to the adder. That doesn't seem to relate to what we're trying to do. The program counter is a register, but it's not register D. Okay, let's try the other one. Let's try the other path going into the multiplexer. The other path going into the multiplexer also goes to, it doesn't go straight to the register bank, but it does go to a demultiplexer that also connects to the register bank. That seems kind of promising to us, right? Okay, so we'll track this down, but in order for this to happen, address mux has to be what? Has to be, okay, what is the input? What is the label of this particular input to the multiplexer? 0. So that means the select has to be 0. Very good. So ADDR mux needs to be a 0. So we'll document that. ADDR mux needs to be a 0, okay, to connect a demux of register bank output 1 to the A port of RAM. I'm just documenting it as we go. Okay, so now we switch back and go like, okay, so this demultiplexer needs to connect the input to this particular output, which means R01 demux needs to be a what? A 1 or a 0? A 0, very good. Okay, because we need this input to connect to output 0. So that means this select has to be a 0. So this is register output 1 demux. We'll write it down here. So we say register output 1 demux needs to be a 0, okay, to connect register output 1 from the register bank to the multiplexer of the A port of RAM. Okay. Okay, so cool. So now we know how to specify the path all the way to here. And then we hit kind of a dead end at this point because out 1 of the register bank, I don't know how to specify what connects to out 1 of the register bank, at least not from the outside of the register bank itself. So what do I need to do next? It's a maze inside a maze, right? Okay, so now that we have solved the outer maze, we now have to solve the inside maze. So we right click and say view register bank, and the positions of the pins are actually correct. So we are basically looking at reg out 1, okay, and we say how do we connect this to register D? In other words, we want this thing to connect to register D. How do we make that happen? Okay, it's solving a maze, right? This is a multiplexer. So with a multiplexer, it has multiple inputs and only one output. And its job is to select which input connects to the output. So which input to this multiplexer connects to register D? The last one, right? Like that? So if the first one is numbered 0, what do you think the last one is numbered? Number 3, which in binary is 1, 1. Okay. So where do we specify that 1, 1 so that it switches input 3 to the output? Register out 1 select. Cool. So that gives us one additional piece of information. So register output 1 select needs to be 1 1 in base 2. Okay. To select register D as output 1 of the register bank. Okay. Huh? 1 1. Yep. All right. Nice. So now we have completed the entire path to connect register D to port A of RAM. Did I use anything that I have not talked about in this class?
Maybe some of the syntax you're using with the mouse pad. I haven't seen those. Are they commands that are going to be in the tactile processor language? Is that where you're seeing a variant of C?
Are you no? It's really just a casual documentation thing to specify which tunnel needs to have what value.
Oh, okay.
That's all I'm trying to do here is to jot down, in order to make that path happen, what do I need to specify for those tunnels? So these are all corresponding to actual names of the tunnels so that I can, do all that stuff. Okay. So we have answered the first question about how the RAM is going to be used. In other words, now we have a way to specify which location in RAM are we interested in. We know it's a write operation, which also means someone has to specify what content we are going to use to overwrite that location. Is that making any sense? Maybe. Okay. So that means we have to zoom out again and look at the main processor, look at the RAM component again. But this time we focus on the D port. In other words, this time we look at the D port and go like, okay, so what should we use to hook up to the D port of RAM to specify the content of the new content of the location that is now going to be selected by register D? Okay, so let's switch back to the original thing that we wanted to do, which is in here. So we focus on this statement or the one before, they're equivalent. So which register do you think we need to connect to the D port of RAM? Register B. So here's our next maze run, to figure out, okay, how do we go all the way from the D port of RAM back to register B in the register bank. Okay. And okay, so I have just highlighted, the D port or the wire connecting to the D port. And this one does connect to a lot more things than the other one. So we just have to kind of look at all these different things and go like, well, can we rule out, certain things in this picture? So I think we can rule out this, connection here because it's connecting to an input of a register. So the D port of RAM connects directly to the input of the instruction register. We can safely ignore that, okay, for two obvious reasons. One is this is an input of a device. It's not going to specify any content. It's not going to be very helpful to us. And two, this is the instruction register. It's not register B. Okay, so we can just go like, not this one. This is the one that we actually need, but we'll take a look at the other path too, because we want to see how we can rule out the other path. The other path, which is the one that's going all the way up, all the way to the left, and then down into this multiplexer. This one can go through this multiplexer and then go through another multiplexer to connect to the program counter. The program counter is not register B. And also, it is only connecting to the input of the program counter, not the output of a register. So there are multiple reasons why this particular wire is not going to help us. So whatever is left is going to be the answer. So we want to track down this one here. Okay? So where is this one going to? This is actually going into the output of a demultiplexer. But we look at the demultiplexer, the input of that demultiplexer does come from the register bank. That looks promising to us. Is that okay? So now the question is, how do we configure this demultiplexer so that the input of this demultiplexer does connect to the data port of RAM? How do we use a demultiplexer? Kind of the same way that we use a multiplexer, right? Except, the direction is reversed. We have one input and multiple outputs. And this one has its own enable as well. So we need to look at RO0EN, register output 0 enable. That has to be a 1 in order for that demultiplexer to be in use. Okay, so that's one thing I'm going to write down is, let's see, put here, register output 0 enable needs to be a 1, okay, to enable the multiplexer that connects to output 0 of the register bank. Okay. And we also need this thing to have a meaningful thing because we need to specify exactly, I think it's this path here, which number is corresponding to this output. 0, 1, and then 2. This is output 2 of the demultiplexer, which also means the select, which is known as register output 0 demux, needs to be a 2 as well, which is 1, 0 in base 2. Is that okay? So now we write it down. Register output 0 demux is 1, 0. Okay, register output 0 demux is 1, 0 in base 2. And this is, to select output 2 of the demux that connects to out 0 of the register bank. Okay. So now we now have a clean path all the way to out 0 of the register bank, and we want that to hook up to register B. But from the outside, this is all that we can do. Okay, we can track all the way to here, and now we have to zoom in into the register bank and say, okay, so how do we connect register B, which is inside the register bank, to output 0 as a port of the register bank itself? Is that okay? So we zoom in, we right click on the register bank, we say view register bank, and we are looking at this wire, and we want to connect this wire to here. Whoops. And well, it seems like the only thing in between is a multiplexer. So now the question is, how do we configure this multiplexer so that the output or port Q of register B connects to this particular output pin? What do you think? We just have to select it, right? So we have to configure register output 0 select to 0, 1 because it's register B. Okay, so we write it down. Okay, so we write down register output 0, and I think from the outside it's called select. It's going to be a 0, 1 in base 2. Okay, so we are selecting out register B as out 0 of the register bank. Okay, and let me just double check on the names of all those ports because sometimes I don't remember the name of the ports. So register output 0 select, and the other one is register output 1 select. I'm not sure I used the right name. Yep, I did. Okay, cool. All right, so when we look into the text editor, everything from line 7 to line 15, because for some reason I didn't skip one line, but the comment was too long to fit on one line. So everything from line 7 to line 15 is what we need to specify the paths from the register bank to the RAM component in order to perform the operation that we want to do. RAM bracket D equals to B is one way to look at it. or you can also look at it as asterisk D equals to B. That is what we need to do. Is that okay? Yep.
Can we go back to the register bank?
The register bank, okay?
So is that the row, the register out slash C1?
So you want to go inside or outside?
Inside.
Go inside. Uh-huh.
And then you said the register out slash should be C1?
This one is 0, 1 to select register B. This one needs to be 1, 1 to select register D. Yep. All right. Are we good so far? So how do we change those bits that we have just mentioned? In other words, we go outside again. So we go back to the main processor view, and we are talking about this tunnel, this tunnel, this tunnel, this tunnel, and a whole bunch on the other side, like RAM cell, RAM load, and there's one over here, address mux. So who's in charge of these tunnels? Sir Topham Hatt. Very good. There are no input pins corresponding to these tunnels. These tunnels, they're all connected to the output of the ROM in the processor. So if you track down this wire, it splits out, splits up into several things. You can see RAM cell and RAM load is basically a component of this wire. And then it also splits up to ucode data or microcode data. That by itself, okay, this is microcode data. This by itself splits out into all of these individual tunnels. So you can see some of these are familiar, right? We can see register output 0 enable, register output 0 select, register output 0 demux, register output 1 select, register output 1 demux, address mux. Those are the things that we have just mentioned. So ultimately, to establish that path, okay, to implement what we wanted to do, is something in the ROM. Something in the ROM just has the right content to actuate the demultiplexers, the multiplexers, to configure the RAM, to configure the register bank accordingly in order for that to happen. Is that okay? And that's why this part is so important, because this is the controller of the entire processor. So if you look at the rest of the design as the island of Sodor, with all the railroad tracks and all the trains and whatnot, okay, this is the controller. This is the Sir Topham Hatt. The guy who is going to flip switches in his office, turn the switches from here to here, tell the train to start from here to here, and so on and so forth. He's coordinating the rest of the entire processor. So are we okay so far with the explanation up to this point? And that was just one of many instructions. So how many instructions do we have? Let's check it out. So we go back to the browser, and we go to the shared folder of this class. Okay, nope, wrong class. So we go back to the share folder, and then within the shared folder, there's a processor subfolder. And for summary purposes, the best document to look at is called the opcode table, which you have already seen in the previous homework assignment. So we take a look at this, okay, double click, there we go. And then we look at the number of instructions here. The first one is called the no-op instruction, and guess what no-op is going to do? I think the name kind of gives it away. No-op means no operation, which means it doesn't do a single thing, okay? It doesn't have any effect, I should put it that way. Halt, now, if you look at the columns, column B is what we call the mnemonics of an instruction, and then column C is what I call is the operational explanation of an instruction, and then column A is the actual binary opcode pattern of the instruction. So when you look at no-op is easy. no op in terms of the opcode, which is a binary bit pattern that the processor can understand. This is the bit pattern that you put into RAM. So opcode applies to RAM, not the ROM. Okay. So the no op instruction has a opcode of 0, 0, 0 in hexadecimal. What does it do? What do you think this notation is saying? Open and close curly brace. What do you do? You know, what do you think your program is going to do when you have a statement like that? It is a statement. It's an empty block, which doesn't do anything. Okay, it would just simply proceed to whatever is next to it and continue execution. Is that okay? Let's look at halt. Halt has a opcode of 0, 1 in hexadecimal, but the meaning is a little bit different. Okay, I'm gonna get out. I'm gonna stop using exit 1 because it really does not do the exit 1. So it really is doing this part here. What is that? 4 in parentheses, 2 semicolons, and then outside is another semicolon. What is that? It's an infinite loop. It's a loop that does not exit. So when you execute the halt instruction, it will never finish the execution of the halt instruction. It's basically the last instruction that you want to have in a program. Okay, so that's what halt does. So we have a whole bunch of other instructions. Add I is not actually implemented, so don't count that one. And then we have jump I, JLI, I, JOI, and so on. And then we have STF, CPR, JL, blah, 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 blah. And eventually we get to the ST instruction. So where's the ST instruction? Okay. I see LD. Nope, ST is right here. So we find the ST instruction here. And you can see it is using the same kind of explanation. The instruction is the opcode starts with 1111, which is F in hexadecimal. And then we got XXYY. Now, from the previous lab assignment, you know what XXYY means. XX is corresponding to this particular X register, which is the one supplying the value. YY is corresponding to Y, which is in parentheses. When something is in parentheses, it is basically syntactically telling you we're dereferencing it. We're using it to control the location in RAM. So in the case of our asterisk D equals to B, YY would be 1, 1, XX would be 0, 1. So the actual opcode would have been 1, 1, 1, 1, 0, 1, 1, 1. So that means it is F7. So F7 is the opcode of what we have just been talking about. Is that okay? Maybe. So part of this is a repetition of what you learned in the previous lab, and part of this is something new. So are we still doing okay or not? If we are not doing okay, then you guys need to ask questions. Yep. Yes, I liked it.
Can you explain the F7 again, where we get that from?
Okay, so the F7 comes, so the F has to be there. So when you look at an opcode pattern, the ones that already has zeros or ones in it, you have to have those. So that means the opcode of ST, of any ST instruction, must start with 1, 1, 1, 1, and that's the F, because that's in hexadecimal. 1, 1, 1, 1 is F. Now where's the 7? We know that the register supplying the value is register B. Register B is the second register, so it's also known as register 1. But register 1 in 2 bits is 0, 1. So that's why we know XX is 0, 1. And then YY specifies which register points to the location that we want to overwrite. We know that's register D, which is also known as register 3. But 3 is in base 10. It's 1, 1 in binary. So YY is 1, 1. So when you combine XX, which is 0, 1, and YY being 1, 1, you get 0, 1, 1, 1, which is 7 in hexadecimal. So that's why we have F7 as the opcode of that particular instruction. You're welcome. So, yep.
If we have more register bank, so the number will be expanded with the individual program.
Correct. So if your register bank contains more registers, I think that's what you meant, then we'll need more bits to specify which register, which also means it's not going to likely to fit in a byte anymore. So that's going to cause a very dramatic change in terms of the opcode and also how things are organized. So I can't really afford to do it, because it's just going to be a little bit cumbersome to do it. Okay, very good. So this processor it doesn't really have that many instructions. Okay, so if you look at all of these things here, we'll do a quick count. So we'll do a quick count. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm just doing an approximate estimate here. Oh, come on. It's not. There are not really a whole lot of instructions. I can do it. I can count it in a slightly different way. I haven't really talked about this part, but it's actually an easier way to count it. So we'll go to cisp310, go to processor, go to opcodes, and then we'll just go look at the ones that are in green. I'm just thinking about how to list those. Well, we can just do a quick count here. Okay, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27. There are 27 instructions. 27 instructions is a very, very, very small number by any means. If you look at the Intel architecture, the processor that's usually running inside a laptop computer, I think it has upwards of several hundreds of instructions. And even if you look at a cell phone, or if you look at the Fitbit, the ARM processor inside those particular devices still has significantly more than 20-something instructions. So the processors that has fewer types of instructions are called RISC processors. RISC, it stands for Reduced Instruction Set Computer. Your Intel processor inside a laptop computer, those are called CISC processors, which stands for Complex Instruction Set Computers. Okay, so at some point we're going to talk about, why do we have these two, what are the advantages to one to the other one, and so on. But today we're just going to focus on the instruction, because you do have a lab that depends on the concept that we are talking about right now. So if I have enough time at the end of the lecture, we can get into that CISC versus RISC discussion. If not, then it's okay. We can push it off to another lecture. Okay, so now we go back to the simulator, and we go like, well, I would like to see the processor doing this. Okay, so I'm going to write the instructions here. It was F7. Okay, that's the store instruction. And we're going to stop the program execution with a 0, 1, which is the halt instruction. Because without a 0, 1 halt instruction, do you guys remember what 0, 0 is? Which mnemonic corresponds to 0, 0 as an opcode? The no op. So it's going to skip, it's going to slide through the rest of the program and then go back to do the F7 again. Okay, so that's not very nice, okay, because we can't really tell whether the program has stopped or not. So that's why, for any program that you write in this class, it's always good to end the entire program with a 0, 1 as an opcode, so that the program would actually just stop there, okay? Well, I think we're ready to run this particular program. Yes?
Could you put that 0, 1 at the very end?
You could. So you basically let all the no-op instructions execute and quote-unquote slide until you hit the halt instruction.
Safer to do it immediately after
Well, I just like to do it like this, just in case I overclock a few times too many, then I stop, early enough. Okay? All right. So now we are ready to run this particular program because we want to actually see the content of register B to be stored in a RAM location that is pointed to by register D. Okay? We actually want to see that happen. To see that happen, let's go ahead and change the register bank. We change the initial conditions of the register bank just a little bit more so that it's a little bit more fun. So we're going to change register B to, I don't know, BF, okay? And then we'll change register D, which controls which location is being overwritten, to, let's try something that's much more obvious. Let's try location 2, which is the 1 byte after the halt instruction. So that should make it pretty obvious when we look at the RAM. We go like, oh, that location used to be 0, and now it is BF. Is that okay? Same instruction, we're just changing the location and the value that we're going to use to override that location. Okay, so now we are going to run the program. All right, so when you run the program, this is a gigantic schematic, okay, compared to anything that we have done up to this point in Logisim. This is pretty complex. So the question is, where do we start? The starting point is always in the ROM, because it is always the ROM that is dictating the rest of the processor. So the first thing we pay attention to is the microcode pointer. So what is in the ROM and what is in the RAM? How do we call these things? What we have in the ROM, they're called microcode. Okay, it's called microcode because it is actually the underlying implementation of the actual opcodes. Where do we store the opcodes? Opcodes are stored in RAM, which is not visible here. Microcode is stored in ROM. Is that okay? So each opcode can be implemented by a series of microcodes. Is that okay? So you get opcode stored in RAM, and then you have microcode that is stored in ROM. When you execute one opcode in RAM, it can go through multiple steps in ROM. And then each step in ROM, or each location in ROM, I usually call it a slice or microcode slice, because that truly is the individual things that you can do per time slice. So that's why I call each one a microcode slice. Okay, that's just my terminology. All right, so we look at this and go like, okay, what is happening here? We know that location 0 is addressed in the ROM, and it has the content of 1080007. But we can actually see, how things are activated and whatnot, right? Because of all the green wires, light green is 1, dark green is a 0. So we can actually check out the entire design and kind of take an inventory of, who is paying attention, who is activated, and who is not, okay? Who is falling asleep right now. So the first thing we want to know is, how is the microcode pointer itself going to be? Is it going to be updated in the next cycle? What do you think? It's a register, so how do we know whether a register is going to be updated or not? What port of a register can give you an idea of whether it's going to update or not? The EN, the enable. Okay, if a register is enabled, it means it is going to be updated. If it is not enabled, then it's not going to get updated. So it does seem like the microcode pointer is going to be updated pretty soon because it is enabled. So if it is going to be updated, then the next question is, how is it going to be updated? In other words, we look at the path. Okay, what path is leading to the D port of the microcode pointer? That's the next question. What do you think? Well, looks like it is coming from a multiplexer, right? So if it's coming from a multiplexer, then the question is, how is the multiplexer configured? Which input of the multiplexer becomes the output of the multiplexer? Well, the select is a 1, which means input 1 is going to connect to the output for this particular multiplexer. That, in return, is coming from an adder. In other words, the microcode pointer is just going to be incremented when it's updated. It's just going to go from 000 to 001. Okay, so that takes care of the microcode pointer itself. It's just going to increment. Okay, what about the rest? What about the rest of the processor? Now, the first time you do this, I strongly recommend that you do not take any shortcuts and actually just go through every single component and see whether they are active or not. The multiplexers and demultiplexers, they're not so important. Look at all the registers, okay? Look at all the registers, look at the RAM module itself, because those things can be enabled or disabled. The multiplexers are only there to help us form a path between the components. But if the components themselves are disabled, hey, who cares about the multiplexers? All right, so we look at the register bank, and does it seem like we're using the register bank at all? I don't see anything being enabled. So this component seems to be resting at this point. What about the ALU? Does the ALU seem to be enabled at this point? It has its own EN pin, which means it can be enabled or disabled. So at this point, is it enabled? Nope. Okay, so we can forget about this. What about the flags register? Is it enabled? Nope. Okay, we can forget that. What about the program counter, which is this guy here? No, not enabled. Okay. So it doesn't seem like a whole lot of things are enabled. And then we slide a little bit to the right. And then we look at the RAM component. Ah, okay, the RAM component seems to be selected. Okay, the SEL is 1, so that means the RAM is is active. If the RAM is active, the next question immediately is going to be, are we reading or are we writing? Okay, so in this case, the LD pin is a 1, so are we reading from RAM or are we writing to RAM? We are reading from RAM. Okay, very good. So that's the second question. Third question, which location? Well, we know it's location 0, but who is telling us that we want to access location 0? Because it has to come from somewhere, right? So how do we do that? We track down port A. So we track down port A and go like, okay, this is going to a multiplexer. The multiplexer has the select being a 1, so we know the multiplexer is selecting input 1, which is this wire. And then we track that one down, and it is the output of the program counter. PC stands for program counter. Now, the program counter is very, very important because what its job is to point to the next opcode to execute. That's its job. Okay? So if you think about it, it is the current page of an instruction manual that you're reading. It's kind of like a bookmark of, okay, where were we at, with the operation manual? Is that okay? So that's why the program counter is really important inside the processor. It tells us where in RAM are we executing. Is that okay? Okay, so now we know, the program counter is dictating which location in RAM we are reading. The next question is, okay, every time you know that you're accessing RAM, you have to ask these questions. The last question is, where is this going to? We know we are reading, which means something should be paying attention to this particular data, which turns out to be the opcode that we were talking about, okay? So you track down the paths, okay, of this particular node, and eventually you will see that it's going into a register called the instruction register, and it is enabled. So that means on the next rising edge, the instruction register is going to be updated. What do you think is the new content of the instruction register? F7. Very good. Okay. So that's the kind of analysis that you have to go through when you single clock through the processor as you execute instructions. This is a lot of work. I understand. This is a lot of work. But as you start to get used to the processor and as you start to get used to the instructions, then it's not going to be as bad. Okay? At some point, you're going to go like, okay, I kind of know what's going to happen with instructions, and I do not need to look at all the individual components anymore. Okay, so we're going to single clock it. Okay, Control T will change the edge of the clock. It will give me a rising edge this time. So you can see at the rising edge, the instruction register is now updated to F7. Okay, just as expected. And nothing else is really changed. This is the only thing that we are doing. And then on the falling edge, the microcode pointer is going to be incremented. The microcode pointer, if you look at it, is the only register of the entire design that has a trigger of falling edge. Everything has a rising edge trigger. The only register that has a falling edge trigger is the microcode pointer, because it has to kind of do it on the offbeat, okay? Because otherwise you'll be pulling the rug under yourself, because you'll be changing the configuration of all the multiplexers and demultiplexers and the components and whatnot, you know, while you are changing this. So that's why this has to happen on the offbeat, so that the rest of the operations can be stable. Okay, so that means, you know, when I Control T again, which means the clock is going to go from a 1 back to a 0, the microcode pointer will change to 0, 0, 1, but everybody else is sensitive to only rising edge, so nothing is going to happen to the rest of the processor. Okay, so we Control T, and voila. The microcode pointer is now 0, 0, 1. So that means, oh, we have a whole bunch of new things going on now. Okay, so we go through this whole analysis again and say, who's awake? What are they doing? How are things connected? We go through the whole exercise again. Well, once you get used to the map, it's not too bad. Okay, so we just go, at first, okay, I recommend that you guys go through an exhaustive search to find out what is activated and what is not activated. The register bank doesn't seem to be in use. Okay, the demultiplexer coming out of it doesn't seem to be in use. The program counter is going to change. See how this, you know, how it's enabled. So we know the program counter is going to be changed. Now, if you know a register is going to be changed, the next question is, how is it going to be changed? So in this case, we look at the program counter, which has an incrementing mechanism like this one here. So the question is, where is the input pin D connected to when it's going to be updated? Well, that's all going to be determined by this multiplexer, right? And this multiplexer has a select of 0. That's why it's going to be coming in from input 0. Input 0 connects to the output of the adder. So that means the program counter is just going to increment when we have a rising edge. Is that making any sense? Why? Because we have just read an instruction. So the previous cycle is called a fetch cycle, where the processor goes to RAM and say, give me the next opcode. I'm going to put it into a register. That is called the fetch cycle in the cycle of executing an instruction. Is that okay? So what this cycle is called the decode cycle. So let's find out what the decode cycle is going to do. Let's see if we're still paying attention to RAM. So let's slide it to the right. We are not paying attention to RAM anymore, because RAM cell is now a 0, which means, you know, I know we are still specifying a read operation, but it's not doing anything, okay? The RAM component is actually sleeping at this point. What else is significant at this point? Let's check out a few other things. Ooh, look at the program microcode pointer. The microcode pointer has an enable of 1 again, which means on the next falling edge, it's going to be updated. But the question is, how is it going to be updated? So we know the program counter is going to increment. We know the microcode pointer is also going to be updated. The question is, how is it going to be updated? So you have to look at the multiplexer. the multiplexer that is controlling what is being used to update the microcode pointer does not have 1 anymore as a select, now has a 0 as a select, which means input 0 of the multiplexer is now used to update the microcode pointer. It is no longer incrementing. It is no longer just saying, oh, I'm going from 001 to 002. That's not what it's going to do. It's going to take the merged output of this splitter as the input here. Okay, so what are we seeing here? What should we be seeing with this merger? Well, the one part of the merger comes from instruction, and the instruction is connected to the output of the instruction register. So we know what that part should look like. It's F7, right? So F7 is going to specify bit 4 to bit 11 of this splitter. But the splitter has a second component, which is bit 0 to 3, and it's a constant of 0. So what do you think this wire after the merge should look like? What is the content of the wire after the merge? First of all, we know it has 12 bits from bit 0 to bit 11, right? We know the upper 8 bits is really just the same thing as what the instruction register has, which is F7. We also know the lowest 4 bits, bit 0 to 3, are all zeros. So what do you think in hexadecimal is going to be the content of this wire? You guys should know that. Okay, well, if you want to, you can write it down, okay? Because, okay, one thing is staring at it is not going to help. So, so what you need to do, if you need to figure out what's going on here, is to actually write it out. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? We know the least significant 4 bits are zeros. 1, 2, 3, 4. Right? We also know the most significant 8 bits are really just coming from instruction. Bit 0 of instruction becomes bit 4 of this wire. Bit 1 of instruction becomes bit 5 of this thing here. Is that right? Okay. But we also know what instruction is. It's F7. So the 7 is 0, 1, 1, 1. The F is 1, 1, 1, 1. So now we know what the wire, the merged wire, should look like. It is F7, 0. Is that making any sense? Okay. So the next thing we do is to double check. Is it really F7, 0? Yep. Okay, cool. Wait. That means we're going to update the microcode pointer from 001 to F70. Yep, that's actually what we're going to do, okay, on the next falling edge. So we are not updating yet because the next transition is a rising edge. So that rising edge is only going to increment the program counter. Okay, so the program counter is still visible here. That's the program counter. So I'm going to do Control T to have a rising edge. So you guys pay attention to the program counter. Control T, program counter increments to 0, 1, which means, yeah, we have fetched the instruction already. So now it is the time to decode that instruction, to decode the opcode. To decode the opcode is really just to update the microcode pointer to go to the location in ROM that corresponds to the opcode that we are trying to execute. Okay, so this is the decode operation. If I want to define the most definitive moment of the decode cycle of executing instructions, this is it. Okay, so when I type Control T again, this is decoding. Control T, pay attention to the microcode pointer and also the ROM here. Control T, blink. That's decode. So first we fetch, second we decode, now we are ready to execute. In other words, what you're seeing in ROM at this point is specific to that ST instruction. You look at this and go like, whoa, that's a whole bunch of hexadecimal digits. 1503982. What does that mean? How do you figure out the meaning of these, of the ROM component? We have done it twice already, so what do? We look at all the components in the processor. We see who is sleeping. We just kind of ignore those guys. And then we see which one is active, which one is ready to update. And then we look at all the multiplexers and demultiplexers to see how things are interconnected. Does that make any sense? So let's go through that exercise. First of all, we look at RAM, okay, because it's easy to see whether an operation is involving RAM or not. Well, guess what? RAM is selected, so we know there are 3 additional questions to ask now, right? Every time we know the RAM is active, we have to ask, are we reading or writing? Which location and what content? There are always those 3 additional questions to ask. Well, okay, so let's answer those questions one by one. Are we reading or writing? Are we reading from RAM or are we writing to RAM? We are writing to RAM because LD is a 0. Okay, so this is the part where studying the component can be helpful so that you don't have to kind of question yourself and go like, is it reading or are we writing? Okay, so you got to spend a little bit of time to study the components themselves. Okay, so we are writing. Which location are we writing to? Well, this kind of gives away the location because that location is highlighted. But why location 2? Who says location 2? Well, we know the address port is specifying the location. But then who is driving the address port? Who is responsible for this? Well, how do we know that, right? So we have to double check. So we look at the multiplexer. The multiplexer says we are selecting input 0 to the output. This is input 0. This is a demultiplexer, which is selecting the output 0. And this is the input. And where's that input coming from? The input is coming from out 1 of the register bank. That seems awfully familiar. Wait, hold on. But who is specifying the content of out 1? Okay, so you can always do this, okay? You can always go into the component. It is telling you that 1 is used to select which register we are using to specify out 1. 1 is corresponding to register D, and register D has a value of 2. Oh, that explains it, right? That explains why location 2 is selected in RAM. Is that okay? But what are we doing to the data port? Okay, because if we are writing, then somebody has to specify the content, the new content, to overwrite location 2. Who is doing that? That's the last question, the third question to ask once we know RAM is being used. So we go to the RAM and go like, click on this thing here and go like, okay, it has the Y itself has a content of BF. But where is that coming from? Well, you guys know where it's coming from because we got one register that has a doctored content of BF. But we have to double check, why is it having BF? So we look at all of these wires that it connects to, particularly this one here. And the reason why I'm paying attention to this guy is because this is enabled. There's a reason why the demultiplexer is turned on, okay? Not only is it turned on, it is selecting a particular output. So let's figure out which output it has selected. So we click on this wire, it is selecting output 2. This is output 0, output 1, this is output 2. So indeed, the output of this demultiplexer is specifying the content to the D port of RAM. Great. So the input of this demultiplexer is connected to the output 0 of the register bank. But who is driving the output 0 of the register bank? We go into the register bank again, and we go like, okay, who is connecting to the output of this multiplexer? Well, if we look at the select, we know, right? The select is 0, 1, which means input 1 is connected to the output, and that input 1 connects to the output of register B. So register B is supplying the content onto the D port of RAM. Register D is specifying the A port of RAM, and we're just waiting for the next rising edge to actually perform the write operation. Okay, so what are we going to do in the next rising edge? Let's go back to the main processor design, and we focus on the RAM component. And once again, we look at, this is specifying location 2, this is specifying the content of BF. So when I have a next rising edge, what do you think is going to happen? It's a write operation. So what location is going to become what? Location 2 is going to be updated to BF, okay, which is the very same operation that we wanted to do from the beginning. But this time, it is not something that I do. I'm not doing anything manually. This is the result of executing an instruction. So this is the whole process of executing an instruction. So switching back to LogicSim, this is another definitive moment. This is the execution of an opcode. So first we fetch, second we decode, and then third we execute. So this is the execution of an actual opcode. Okay, so observe this location as I type Control T on the keyboard to single clock or to change the edge of the clock. Control T, blink. Yay! What are we going to do next? We're not done yet. we are not quite at the halt instruction yet. So the next thing is going to be a falling edge. And we know who is sensitive to a falling edge, right? The microcode pointer is sensitive to a falling edge. And it is also enabled. So now we have to ask, how are we updating the microcode pointer this time? The microcode pointer's input is connected to the multiplexer. The multiplexer is selecting input 1. Input 1 is this time just coming from the adder. So that means we're really just incrementing the microcode pointer. The microcode pointer should go from F70 to F71. Is that making any sense? And it's going to do it on the falling edge because the microcode pointer is the only register that is sensitive to a falling edge and not a rising edge. Are we still doing okay so far? Yes? Okay, so all eyes on the microcode pointer and the ROM, okay? Because we're expecting the microcode pointer to go to F71, and then the next location gets highlighted. Control T. Whoa, 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 what just happened here? I really should use the Doctor Who line of, do not blink. Okay, so what just happened here? I think the weeping angels that just did a trick on us. If you don't know the reference, you have to watch Doctor Who. Just look up weeping angels and Doctor Who, and you will find references of what that is all about. So what just happened? You know, why are we back to location 000 instead of F71? Well, maybe it has to do with what is actually at locations F71. So what we do now is to go to the ROM component and say, show me location F71. Okay, so we just slide all the way to the end, F71. Okay, so here is F70. This is F71. F71 doesn't look very imposing, right? It's got a whole bunch of zeros and a single 2 as the most significant hexadecimal digit. Doesn't seem very, doesn't seem like it's going to do much. But let's figure out what this is going to look like as a bit pattern. Okay, so instead of looking at it as a hexadecimal number, let's look at it as a binary number. Each 0 is 4 bits. Okay, so we just count. Okay, there are 6 zeros that accounts for 24 zeros in binary. 2 itself is 1 0, which means it has one extra 0 and then a 1. So we have altogether 25 zeros and a 1 as the most significant bit. Is that okay? So that means the 1 is corresponding to bit 25, not 26 because we counted from 0. So bit 25 is the only one that has a 1. Everybody has a 0. But how does that impacting the processor? That's what we want to know. So we look at this and we go like, okay, so we know that in the previous cycle, the most significant bit is a 1. Everything else is a 0. So we focus on bit 25. Bit 25 was a 1, okay, and it goes into an OR gate. The output of the OR gate goes, guess what, to a pin labeled 0. What does that do to a register? It's reset, which means when this port of a register is a 1, the register is reset to 0. That is why we went from location F71 boop, back to location 000, because the microcode at location F71 says reset the microcode pointer to 0. So tell me again, what was the first step of executing an instruction? Fetch. Okay. So where are we going to fetch this time? And which register is specifying where we are fetching the next opcode? Come on, you guys know the answer? The program counter. Okay, so we look at the program counter. The program counter now specifies location 1, which makes sense, right? Because we just executed the opcode of location 00. So now we are expecting location 1 to be read. It is being read because RAM is selected. It is a read operation, and the instruction register is being updated. Okay, and what is it going to be updated to? 01, which is the opcode of the halt instruction. Okay, so we do a Control T, it gets updated. Okay, and then we have a falling edge. The falling edge is going to update the microcode pointer to 001, like so. And this is the second phase of executing an instruction. It's called the decode operation. So the decode operation is really easy. Okay, if you think about it, it's easy. All it's going to do is to say, whatever the opcode is, just pad a 0 in hexadecimal to the right-hand side. If the opcode is 01, then we go to location 010 in ROM. Okay, that's all it's going to do. So, and we're also going to increment the program counter, because as far as the program counter is concerned, location 1 is now done. So we do a Control T, and you can see how the program counter is now ready to get the next instruction from location 02. And we can also see how the microcode pointer is going to be updated to 010. Okay, because when we click on the wire going in, it is already 010. Okay, so we do another Control T. So now we go to location 010. Location 010 in the ROM has all zeros, which means everybody is taking a nap. Okay, if everybody is taking a nap, what do you think is going to happen? When I say everybody is taking a nap, that includes the microcode pointer itself. Look at the microcode pointer. Oh, it is enabled, okay. It is enabled, and it's going to be updated to what? What do you think the microcode pointer is going to be updated this time on the falling edge? The rising edge is not going to do anything because remember, the rest of the processor is rising edge sensitive. But nothing is on because you can see the pattern is all zeros. So we know the rest of the processor is not going to do anything. The only thing that is still actively being updated is the microcode pointer itself. But what is it? How is the microcode pointer going to be updated? Well, let's check the multiplexer, right? The multiplexer is still selecting 0. 0 is here. And so we are going to use 0, 1, 0 to update the microcode pointer on the next falling edge. So how is that going to do anything useful? It's not going to do anything useful because the microcode pointer is 0, 1, 0 already. So we are just overriding the microcode pointer from here on to 0, 1, 0 all the time. Nothing happens. In other words, the documentation of the halt instruction of forever do nothing is actually appropriate because we are now stuck here forever. So that concludes the execution of this tiny little program. So is that okay? I know this is a lot of stuff, okay? Which means, you have to go through these steps on your own a few times to start to actually, connect all the concepts. And take notes on the side, when you're doing this, because, trust me, the next 8 weeks or so is all about doing this kind of stuff. Okay? So it's better to get familiarized with the processor just by looking at all the components and understand when which component becomes active. Okay? So I'm going to release the lab for today, and you have until next class or the day of the next class to turn it in. So if you cannot finish it today, it's not too bad. Okay, you still have plenty of time to do it. But I would try to at least get started and hopefully get it done today. Yep. Access code is LDI, but I haven't enabled it yet. So I'm going to go to the lab, and so the next class can come in, and then we'll get it started.